Alrighty, video 3 on 5.5, integration by substitution, also called integration by U substitution. There's nothing magical about using the letter U. It just happens to be sort of our catch-all when when we're trying to either identify or substitute in for some expression of the independent variable. Let's go ahead and just jump right in with a couple of examples. These will, of course, be a little bit more difficult now that we've laid the groundwork, but we'll just sort of work through them one by one. Okay, so let's say we have tangent x dx. Where's my u? Well, this is one of those times where remembering your trig would be really, really helpful because you need to remember that tangent is sine over cosine. Okay. Now, that is pretty helpful since cosine is the derivative of sine and negative sine is the derivative of cosine. It's now in a rational form, and we need to start asking ourselves a couple of questions. Those of you who are already ahead of the game have recognized the fact that this is going to be natural log. So I know that my u is my denominator. My du winds up being negative sine x dx. So what we need to do here in order to change it is just tack on a negative inside, but of course we need to negate that or nullify it by putting a negative outside as well. And this winds up being negative du over u. Okay? Well, that really isn't all that hard. It becomes negative natural log of the absolute value of cosine x plus c, but of course using the properties of logarithms, some people prefer to talk about it in terms of natural log of secant, because remember you can take that negative or whatever that coefficient is here out in front of the natural log and pop it up as the exponent of your argument of your logarithm. And that winds up being the integral of tangent. Now, analogously, of course, if you have cotangent x dx, that becomes cosine x over sine x dx, and that, of course, becomes the natural log of sine x plus c by the same logic. Okay, let's go ahead and let's look at, oh, that'll be a fun one. So I have e to the x over 4 minus e to the x dx. Okay, well, it's rational again. Now, the question is this undoing of the power rule by pulling it apart? Is this natural log, or is this inverse trig? Well, let's go ahead and let's just kind of suppose that this is, let's go ahead and suppose that this is sort of a weird variation of being able to split it apart, because if I actually take the denominator, okay, and turn it into this, and then turn the numerator into du is equal to negative e to the x dx, then what happens here is this, okay? I have, if I just put a negative here and a negative out here, I have negative du over u, okay? Now, obviously, that winds up being natural log. I was actually, yeah, let's just go ahead and do it like this. Let's go ahead and do it by natural log. I was actually just sort of trying to figure out if there's sort of a creative way of doing it by reassessing it in a different way, but I don't think that there is. Yeah, okay. And from here, obviously, it's just a very easy natural log absolute value of u plus c, whereas it's negative natural log. And you do actually have to keep the absolute value bars here, because 4 minus e to the x remember that is negative e to the x plus 4. So that winds up being, taking this, basically that winds up being that. Okay, so there actually is an area where that can be negative, and therefore you do need the absolute value bars. But that would be your integral right there. Okay. Well, let's go ahead and look at a variation on one that we've actually done before. So we have square root of arc sine x 1 minus x squared dx. Well, it's a little bit more difficult. The form is not quite as straightforward. I'm having a hard time seeing my u, but it kind of reminds me of this one that I did earlier. Right? It kind of reminds me of that one. So let's see if I can change the form to illuminate a little bit more the actual form that's going to be helpful for us. Okay, well remember that if I have a radical of a quotient, that actually can be redone as the quotient of two radicals. And so let's go ahead and turn this into that times 1 over the square root of 1 minus x squared dx, and then all of a sudden it's becoming very, very apparent what I need to do. Okay, this over here is obviously my du if my u is arc sine x, right? Remember, u is arc sine x. Du winds up being 1 over the square root of 1 minus x squared dx, or you can plot the dx up in the numerator, it doesn't really matter. So that winds up being u to the 1/2 du, and that has done a great job of taking something that was notationally rather complicated and making it very, very easy. So that winds up being 2/3 u to the 3/2 plus c, or 2/3 arc sine of x to the 3/2 plus c. And that winds up being my integral. Okay, well, let's keep going. Let's do this one. Let's do x squared 3 minus x dx. Well, here I have a problem, okay? I recognize that if I go with my default and make my radicand equal to u, I have a problem, because when I differentiate this in order to get my differential, I get du and negative dx, but I have this strange x squared just sort of lingering around, okay? And the x squared is not accounted for in either one of these. So here's what we're going to do. We're actually going to do, I don't know what the official term for it is. I've always referred to it as back substituting because I had to think of a name for it on the fly, and I seemed as good a name as any. I'm going to use a different variation of that relationship to plug in for x. So I know that if u is equal to 3 minus x, x is equal to 3 minus u, and x squared is equal to u squared minus 6u plus 9. Now, you might think that that's actually taking a step backwards, but once we actually plug in everything, the negative out here, remember, negative dx, I recognize the fact that this has an advantage over the original because this radical is a monomial, which means that it can then be distributed. And that becomes u to the 5/2 minus 6u to the 3/2 plus 9u to the 1/2 du. And from there, I can go ahead and integrate term by term, and it winds up actually being relatively straightforward. That winds up being 2/7 u to the 7/2, or negative 2/7, That winds up being positive. Well, I know this is going to be 5 halves, which is going to be in the denominator. So 2/5 times 6, that's 12/6, or 12/5, sorry. 12/5 u to the 5 halves. And of course, this is now positive because you've distributed this negative. And this winds up being negative, and of course that winds up, of course, being 3 halves, but that's in the denominator, so it winds up being 2/3. 2/3 of 9 is, of course, 6 plus c, and then the only thing that's left to do is just plug in this binomial right here in for all of the u's. Okay, and we get negative 2/7, 3 minus x to the 7 halves plus 12/5, 3 minus x to the 5 halves. Let's see if I can do this without running off the edge of the paper, and Yahtzee. There we go. Now, this is where integration by substitution does indeed get a little bit tricky, because you have to see the back substitution. It's not quite as straightforward. It's not quite as methodical as the way that we've been doing it in the past. But, you know, once you actually have seen it a couple of times, and in fact on your homework done it a couple of times, you should be raring to go with that sort of thing. Like I said, this is going to be just a general smattering of random examples. So let's go ahead and do the next one that I've highlighted on this worksheet that I've pulled off the internet. And I have sine squared x cosine x dx. Okay. Now, here's the thing. Most of y'all probably see that, but we've got to remember that sine squared x is lazy man's notation for sine x in parentheses, the whole quantity squared. And if it were like this, it would be even easier to identify your u as sine x, and of course your du as cosine x dx. Once you've done that, of course, that winds up being u squared du. That gives me 1/3 u cubed plus c, or 1/3 sine cubed x plus c, and that is your integral. And notice that as you start going through these, you can get a kind of a rhythm going on, and you wind up seeing them a whole lot faster. Like anything, it's just a matter of practice. So I have 1 over x natural log x dx. That's a tough one. It's rational. It's got a monomial denominator, but it's got nothing but a 1 in the numerator, on top of the fact that that monomial denominator is a product function of 2 different classes of functions, the x being from the polynomial family, natural log x, of course, being from the logarithmic family. I feel like I'm kind of stuck, right? But here's the thing. At this point, we should know that there are 1,000 different ways of changing the form without changing the value. This is actually a relatively easy integral. Once you rewrite it like that. Okay, you can actually pull that x up and have it be 1 over x in the numerator. It's the same thing. And all of a sudden, you go, well, if my u is natural log x, then my du is 1 over x dx. That winds up being du over u, or natural log u plus c, absolute value, of course. So that's the natural log of x, actually you need to keep those absolute value bars, plus c. And all it took was just a minor changing of the form in order to get it here. Okay. How about tangent cubed x times secant squared x dx? Well, it's going to be a whole lot easier if you can look at that and see that. Okay? Because once u is defined as tangent x, you should have, and your clue is the fact that secant squared is a recognizable derivative, and it's sitting there right next to the dx. Secant squared x dx, that winds up being u cubed du, or 1/4 u to the 4th plus c, which is of course 1/4 tangent to the 4th x plus c. Okay. Here's the thing. That can actually be done more than one way, and at the beginning of the next video, I will show you how. Okay.